Hello and welcome. Today we're going to dive into a chemical mystery that's happening all around you, every single day. I mean, from the food you eat to the soap you use. We're talking about the absolutely fascinating world of acids and bases. You know, we've all been there. That really uncomfortable feeling of acidity after a big meal. So you reach for a remedy. But which one's the right one? Lemon juice? Vinegar? Or maybe some baking soda? Well, choosing the right one actually depends on understanding a really fundamental chemical principle, and that's exactly what we're going to uncover.
So let's meet our two main players in this story. On one side, we've got acids. You definitely know them from the sour taste of a lemon. And on the other side, we have bases, which tend to be bitter, kind of like baking soda. These really distinct tastes are actually our first clue to their secret chemical identities.
Our investigation starts in a place we all know pretty well, the kitchen. Turns out it's the perfect laboratory for figuring out how these substances behave and how we can tell them apart without, and I really strongly recommend this, tasting them.
Okay, so for not using our sense of taste, how do we identify our culprits? We use something called indicators, and you can think of them as little chemical detectives. These are special substances that change color the moment they come into contact with an acid or a base. And what's cool is that nature is full of them, like the dye from a plant called lichen, which gives us litmus, or even a simple kitchen spice like turmeric.
And this is where the evidence becomes crystal clear. Check it out. Blue litmus paper turns red in an acid, while red litmus paper turns blue in a base. Other indicators, like phenolphthalein, go from totally colorless in an acid to this vibrant pink in a base. Every single reaction is like a chemical fingerprint, giving us a positive ID.
But hold on, not all the clues are visual. Some of our chemical detectives actually work with smell. These are called olfactory indicators. The characteristic smell of an onion, for example, you can smell it just fine in an acid, but it completely disappears when you add a base. The same thing happens with vanilla and clove oil. It's a completely different way to solve the very same mystery. Okay, so we know how to identify acids and bases now, but let's see what happens when they actually get to work, starting with some of their most classic reactions. You know, when an acid meets a metal, a very predictable reaction happens every time. The two of them combine, and in that process they produce a compound called a salt, and they release a gas, hydrogen gas. This is just a fundamental rule in the world of acids.
And this illustrates that reaction perfectly. What you're seeing here are zinc granules being dropped into sulfuric acid. See those bubbles fizzing up to the surface? That's not just fizz. That is pure hydrogen gas being created right before our eyes. It's chemistry in action. So how do we prove those bubbles are hydrogen? Well, there's a simple, super classic test. If you capture that gas and bring a burning candle or a splint near it, you'll hear this really distinct pop sound. That's the signature sound of hydrogen combusting, and it is our definitive proof.
And all of this brings us right back to the solution to our original problem, that feeling of too much acid. The remedy is a reaction called neutralization. This is where an acid and a base meet up and essentially cancel each other out, leaving behind a neutral salt and just plain old water. It's the ultimate chemical balancing act. This right here is the key formula. A base plus an acid gives you salt and water. This is exactly why a mild base like a baking soda solution can soothe an acidic stomach. It's not magic, it's a neutralization reaction happening right inside your digestive system. So we've seen them on their own, and we've seen them react. Now let's dig a little deeper into the actual moment of contact to really understand the secret behind their power.
And this brings up a really important question. We've seen that all acids turn blue litmus red, and they all react with metals. But why? What is the one thing they all have in common that gives them these signature acidic properties? This simple experiment gives us our biggest clue. When you dissolve an acid in water, the solution can actually conduct electricity and light up a bulb. Now, this only happens if there are charged particles, or ions, moving through the solution. This, right here, is the secret to their behavior.
And here it is, the secret revealed. The defining feature of any acid is that when you dissolve it in water, it releases positively charged hydrogen ions, or H+. And for a base, it releases negatively charged hydroxide ions, OH-. This release of ions is what gives them all their power. Now, for just a little more detail, these hydrogen ions, the H+ ions, they're so reactive they don't just float around by themselves. They immediately grab onto surrounding water molecules, and they form what's called a hydronium ion. So whenever we talk about H+ ions in a solution, this is the form they're actually in. So it really all comes down to the ion. This one tiny charged particle is the key that unlocks all the properties of both acids and bases. Let's explore that idea just a little bit further.
Since this is all about the concentration of hydrogen ions, it makes sense that we'd have a way to measure it. And that's where the pH scale comes in. It's a scale, usually from 0 to 14, that gives us a precise number for what our senses and indicators can only kind of hint at. The P actually stands for potens, which is German for power. So it's the power of hydrogen.
And this illustrates the whole spectrum just beautifully. Using a special kind of paper, we can actually see the pH of everyday things. I mean, look at the deep reds of highly acidic stuff like stomach acid, moving through the yellows and greens of things like milk and pure water, all the way to the deep blues and purples of strong bases like drain cleaner.
So the code is actually pretty simple to crack. A pH value less than 7 is acidic. Exactly 7 is perfectly neutral, like pure water. And anything greater than 7 is basic, or what we also call alkaline. And the further you get from 7 in either direction, the stronger the acid or the base is. So why does any of this matter? Well, because life as we know it depends on a really delicate pH balance. Our own bodies have to maintain a pH between 7.0 and 7.8 just to function. Even a tiny shift can be dangerous. And the same goes for our environment. When rain becomes too acidic, with a pH less than 5.6, it can be totally devastating for rivers and lakes. And to put that into perspective, just think about another planet for a second. The atmosphere on Venus isn't made of water vapor like ours is. No, it's made of thick, swirling clouds of highly corrosive sulfuric acid. It's about as hostile to life as you can possibly imagine.
Which really leaves us with a final thought. We've seen how a precise pH balance is absolutely essential for life here on Earth. So when we look at a planet like Venus, a world literally wrapped in acid, what does that tell us? It's a stark reminder of just how special and maybe how fragile the chemical balance of our own world truly is.